Everyone. Welcome to our meeting today. We are very happy to have Professor Horacio Ferriz as our guest lecturer for today. Professor Horacio Ferriz is a geological engineer with more than 40 years of professional experience. He is now the professor of exploration geophysics and physical oceanography at the California State University Stanislaus in the United States. We are very happy that Professor Horacio is a good friend of us, good friend of STMKG, good friend of BMKG, and good friend of our director, Professor Dwi Korita Karnawati. And thank you very much, Professor Horacio, for making this guest lecture possible. I know you are very happy to share to our students. Thank you very much for your time, for your attentions, and many things. And now we will hear from Professor Horacio about the use of the radar, high frequency radar, to monitor the tsunami, which is very important for BMKG. We are now living in the subduction zones area in Indonesia, so we are prone for the tsunami occurrence in our country. So this topic is very important for us. And Professor Horacio, you will have like about 30 to 40 minutes lecture, and we will follow by about 20 to 25 minutes for questions and answer for students.
Yes.
Okay.
Thank you, Professor Dimas. That is my plan. I don't want to just talk. I want to hear from you. If you have any questions, please put them in the chat. Professor Dimas is monitoring the chat, and he will let me know if there's something that needs clarification. I will also try to speak slowly so that it is understandable. Let me share my screen. And go into my PowerPoint here. You have a copy of this PowerPoint.
Yes. Perfect.
Professor Dimas has a copy of that, and please feel free to get it from Professor Dimas. I also sent a couple of other papers that I think would be interesting to you. So, as Professor Dimas mentioned, my name is Horacio Ferriz. Most people call me Professor Horacio. And I am a geological engineer by training. That means I use my knowledge of the Earth to solve problems that are meaningful to society. This is the first of a series of lectures that we are coordinating or organizing between my university, California State University Stanislaus, we nickname it Stanislaus State, and the School of Meteorology, Climatology, and Geophysics of Indonesia, which I normally call STMKG, and of course the Bureau of Meteorology, Climatology, and Geophysics, BMKG, which I feel very friendly toward. I chose this particular view of the Earth because it shows the three passions in my life. One of them is the solid Earth. Every time I look at a satellite image of the Earth, I wonder about the mountains, how they form, why does India have this particular shape, what caused this big rift on the east side of Africa, why is it that Sumatra and Java are not just one long archipelago, but have that kink. But I'm also fascinated by the ocean. The ocean is what makes our world different than any other world, and the atmosphere, because the ocean and the atmosphere are coupled, so all those beautiful swirls of clouds do have a connection to the ocean. Today, I'm going to talk about the use of high-frequency radar in tsunami monitoring, and I will give my thanks toward the end of the talk, but I want to tip my hat to Dr. Swaidi, the chief of station of the Padang Pajang station of BMKG, who was my companion as I traveled through Sumatra in this last August, and who introduced me to the the issues that Sumatra and the people of Indonesia are facing. And he is the one who introduced me to this idea of using high-frequency radar in tsunami monitoring. Just to repeat something that you probably already know, tsunamis are trains of waves that are created by a sudden change in the volume of an ocean basin. And there are many reasons why this can be so. One cause is a fault that breaks the floor of the ocean floor, and that causes a change in the volume. And related to that, there should be another casing here in the subduction zone, like you have off the coast of Sumatra and Java, in which the overriding plate pushes against the underriding plate, what we call the megathrust, and that causes a change in the volume of the ocean basin. This would be more the case, say, of the West Sumatran Fault. These two origins of tsunamis probably represent about 80% of the tsunamis that we see generated in the Pacific Basin. However, we also have to take into account submarine landslides. And this is true because most of the islands that are present in the Pacific or the Atlantic are very steep-sided, so their flanks are not very stable. Then we have the cases of volcanoes like Anak Krakatau in Indonesia, which can generate a tsunami. And then in the Cretaceous, there was a big meteorite impact that hit the Gulf of Mexico near the peninsula of Yucatan, and that caused an enormous tsunami that flooded most of northern Mexico, Texas, and all the way up the Imperial Cretaceous Seaway, all the way up to Montana. Now, the thing with tsunamis is that when they are out in the open sea, they have very long wavelengths, 100 to 200 kilometers, but also have very low amplitudes, 1/10 of a meter to a meter, 1/2 a meter. And so they are very difficult to detect, because if you were in a boat in the middle of the ocean, by the time a 100-kilometer long wave bobbed your boat by 1/2 a meter, you would have barely noticed it. They also happen to be shallow water waves, and so they drag along the bottom of the oceans, and that limits their celerity, their speed, to about 700 kilometers per hour. Also, because they are dragging against the floor of the ocean, they are easily refracted or reflected from mid-ocean ridges, from transfer fault scarps, from islands, and that complicates the issue. And normally what would happen at the point of origin is there's going to be a change in the volume of the ocean basin that would create that very long wavelength with very small amplitude. But as that wave approaches the shore, it slows down because of friction against the shore. And since the waves cannot merge with each other, they bunch together. And the only way to accommodate that volume of water is by increasing the amplitude. So by the time they come to the shore, they have indeed very large amplitudes, which is the problem, because with very large amplitudes, they can actually advance onto the shore for a very long distance. So while at sea, as I said, wavelengths of 100 to 200 kilometers, they're moving fast. So an earthquake off the coast of Chile would arrive to Japan after 24 hours. But the main problem is, as they approach the shore, their wavelengths become shorter, maybe 10 kilometers. Their amplitudes become larger, 1 to 10 meters, and their celerity slows down, their speed slows down, but it's still pretty significant at 35 kilometers per hour, for example, so that they can approach the shore relatively fast. Not super fast. At 35 kilometers per hour, we may have 3 hours to evacuate people if we are ready for it. So because they're such a significant hazard, we have all sorts of scientific means to detect that sudden release in, or that sudden change in volume. As I mentioned, 80% of them are related to earthquakes, so an easy way to track those are to have seismometers, because the seismic waves move so fast through the earth. We can identify an earthquake happening within, a few minutes. And then if the wave is going to take 24 hours to cross, well, we have plenty of time to try to track it. But it's a very small wave at sea, so we can use bottom pressure sensors that are anchored in the bottom of the ocean, and they can detect that small change in the elevation of the surface of the water. Of course, they are combined with all sorts of other wind and currents and storms. So we need to do a Fourier deconvolution to find out that very long wavelength wave. And nowadays we have satellites that measure altimetry very precisely, so that's one way of doing it. But we're not measuring a big difference. Remember, just barely a half meter mixed with all the other turbulent movement of the ocean. As they approach the shore or maybe an island, a tide gauge is a very useful way of detecting that arrival of a big amplitude wave. And all these things have to be related to some sort of warning center where all this scientific information can be processed, because from there it has to go to the civil authorities. The civil authorities are the ones that are in charge of protecting their communities. And we have an initiative to create tsunami resilient coastal communities that I know Indonesia is working really hard at it. But basically, we need that capacity building, that education step in which complicated science has to be translated in terms that the civil authorities can understand and can assess to determine whether the probability of a tsunami is high, and they have to move people around. Well, there's one more tool that we can use for that, and that's radar. Radar can send a beam onto the ocean, and if the beam is angled just right, we are able to detect the increase in velocity of a wave as it approaches the shore. And that's what this talk is about. This talk is about the use of radar in order to try to detect an incoming increase in speed because of the push of a tsunami. Basically, what happens, starting down here, is that as the water depth decreases from maybe 4,000 meters, at which point you have 200 meters per second speed, about 700 kilometers per hour, as the depth of the water decreases, so we're going left in this graph, the velocity of propagation of the wave train decreases. And by the time you reach the edge of the continental shelf at about 200 meters depth, the velocity decreases to about 40 meters per second, which, I mean, it goes from 40 to 20 to 10. 35 kilometers per hour is kind of a good average. Now, what happens is, as the waves approach the shore, they become closer together and the amplitude increases, and the water that is being pushed forward is being pushed forward a little faster than the water that is being pushed backward. As the wave passes, you normally have forward movement and then backward movement and forward movement and so on. The trick is, can we detect that increase in velocity, that small increase in velocity? Let me suggest that when you have the additional push from the tsunami, we ought to be able to detect a small increment in velocity. And that's what we're trying to do here. Let me escape this and go to YouTube here. and show you what happens here. You see the particles as they move, as they are pushed, they're beginning to move forward. So this forward motion is what we're trying to detect using radar. Okay, let me quit that, go back to the presentation. Let's move on, slideshow. So how are we going to do that? Well, let's review some basics. First of all, we have to create a radar wave. A radar is an electromagnetic wave, and for reasons that I will explain to in a moment, what we want is a wave that is polarized, that the electrical field is polarized in the vertical plane. So normally when we talk about electromagnetic waves, we understand that there is a magnetic vector, and perpendicular to it, there's an electric vector, an electric field. So as the electric field grows, the magnetic field grows in one direction. As that magnetic field decreases, the magnetic field drops. As the electric field increases in the opposite direction, the magnetic field grows in that direction, and so on and so forth. And the way to do this is to use a monopole antenna, a stick, basically, that has a wire going up. Sometimes it goes up and down and up and down and up and down to reinforce the signal. But basically, when we pass an alternating current up and down, magnetic field, circular magnetic field is generated around that antenna. And when we look at it at a distance, you realize that in that field, the electric vector is perpendicular to the direction of propagation in the vertical sense, whereas the horizontal vector is parallel to the propagation of the vector. I see that Ferry has raised your hand. Please turn your camera or your microphone on and ask the question. Okay, and there's a chat question. Okay, I'm going to let Professor Dimas deal with questions right now so that we're not all waiting. But if you want to talk, just turn your microphone on and ask the question.
Yes, for students, if you have any questions, just raise your hand or you can write your question in the chat room. Anggun, do you have questions?
From now on, no, Mister.
Okay, how about others?
Not yet, sir.
Okay, Professor Horacio, I think you can continue for a while.
I'm going to continue. Save your questions. We'll have time to ask questions later, okay? So the first thing is how we generate the radar signal. The second question that we're interested in here is the frequency. Now, we call this high-frequency radar, and here you see the frequencies increasing toward the top. So here is our high-frequency radar, and then toward the top, you have the infrared and the visible, the UV, X-rays, and gamma. Why is this called high frequency when it is at the bottom of the pile? Well, it's a historic reason. At the time, that was the highest frequency that could be generated. There's our antennas, our monopole antennas generating the high frequency. So in gigahertz, what we use is frequencies of 0.003 gigahertz, about 3 megahertz or 3 megahertz, or 0.03 gigahertz, which is the same as 30 megahertz. In a moment, I'll show you that there's even lower frequencies that we use. So we are in that range there, that little yellow range. This, unfortunately, is flipped upside down. As I said, if you keep increasing the frequency, you get into the infrared and the visible and so on. Here is also the frequency increasing toward the top. There is the HF radar. There's other frequencies we use in radar, ground penetrating radar. And if we go up that way, there's infrared, visible, ultraviolet, X-rays, and gamma rays. But we could also go down in frequency, and then you end in the 20,000 hertz or the 20 kilohertz. We have what we call very low frequency. And that's a type of radar that we use for electromagnetic exploration. And there's even lower frequencies that we use in mineral exploration. So for the people that were used to this particular frequencies, this seemed a very high frequency. It's historic. Now, the important thing about the HF radar is that it has the right wavelength. I'll cover that in a moment, so that as it moves over the surface of the ocean, it almost matches the frequency at which the waves are coming. And that allows it to couple with the surface of the ocean. Notice here, if we're in the HF radar frequencies, the seawater has a resistivity of 0.1 ohms meter. I remind you that resistivity is the inverse of conductivity. So seawater is a very conductive medium, and the radar signal cannot penetrate more than 10 centimeters into it. So it's trying to diffuse in here, but it can't. So it follows the surface of the ocean. And effectively, what we have from our antennas are one beam that goes into the troposphere, and there it gets reflected by all sorts of clouds and temperature inversions. There's another beam that goes and penetrates into the stratosphere and bounces off the ionosphere, and that gives us the very long-range radar. But we have the HF radar that actually hugs the surface of the ocean for a good 100, 200 kilometers. That's what is important to us. The other thing that we need to know, this kind of basic information, is that when you have a series of waves and you're shining an electromagnetic beam onto them, you have reflection. Now, this is called Bragg scattering or the Bragg effect. The Bragg law is actually a law that talks about the diffraction of X-rays on crystal lattices. But it turns out there's also reflection. And I did this little experiment, and I apologize for not cleaning my CD. It was dark and I was half asleep. I took a flashlight and I shone a beam of light on a CD, and of course a CD is lots of little waves very close to each other, and you notice that there's a very strong reflection, in this case in the blue portion of the spectrum, in the very high frequency portion of the spectrum, for those waves, quote unquote, that are close to the source of the electromagnetic radiation. But there's a secondary reflection now in the red portion of the spectrum that comes from waves that are farther away from the source. You'll notice also that this blue reflection is kind of turning to green. Those are secondary reflections that come from the Bragg scattering effect. I will remind you of this fact in just a moment. The last thing that we need to understand is that radar is really good at detecting the Doppler effect. The Doppler effect is a change, a shift in the frequency of a reflected wave if the source of the reflection is moving with respect to the source of the radar. And in the United States, so in this case, this red dot is moving toward the left, which is where the source of the radar is. So the frequency moving away into the source or toward the source gets shifted. The waves get compressed. Whereas away from the source, the waves would get stretched. We're not interested in that right now. We're interested in this part. So in the United States, the police uses this very often to measure the speed of incoming cars. They send a radar beam and that radar beam bounces off a moving car, but because the car is moving, that causes the reflection to have a lower or a higher frequency than the outgoing image, and then you have a receiver here in this unit that detects that shift in the Doppler peak. All right, I think we have all the basics covered. So this is the idea. In the HF radar antenna, we can choose what frequency we broadcast by how fast we're moving the alternating current. So in the WERA system, which is frequency modulated continuous wave system, what they have figured out is they will generate a radar wave with a frequency of 30 megahertz, which works out to a wavelength of about 10 meters. Now, because of Bragg's law, the returning frequency is going to be the ongoing frequency over 2 times the cosine of theta. But because this wave is impinging parallel to the surface, theta is 0, cosine of theta is 1. So it turns out that the reflecting surfaces have a wavelength of 5 meters. So as we send out this signal, it gets reflected from those waves that have exactly 5 meters wavelength, and that's what we receive in the antenna. Now, we have all been in the ocean. The ocean is messy, it's irregular, and there's ups and downs and ups and downs. But as you probably know, all waves, water waves, are additive. That means that complicated wave that we see here is the summation of different waves that have different wavelengths. The tide, for example, is an important one. And of those many waves, there's going to be some, no, I cannot see in my screen, sorry. There are going to be some that are going to be at exactly 5 meters wavelength. Now, that means that in this complicated spectrum, there is a signal that comes from 5 meter wavelength waves. And that's what is being measured by the radar. And I mean, we don't have to do it at exactly 30 megahertz, but that's what the WERA system uses. So, oops, sorry. This is a typical setup for the WERA system. Now, I have to tip my hat to Helzel Messtechnik, a German company who has helped me a lot in understanding this process. But this is their setup. So in this setup, whoops, hold on. You have an antenna. This is what is generating the signal. And remember that stick that we saw, stick figure. So there is circles of signal that are coming out of each one of these antennas. When you have 2 together, they just add their power, so they have more power going out onto the ocean. Sometimes there's a third antenna here to add to that. In the WERA system, they choose to have 2 other antennas, partly to cancel the waves that are coming this way. We don't want those waves. And then we have the receiving antennas, which are normally an array, a line array of antennas, 8, 12, 16. And they are there to listen to the returns of the radar system that is, or of the radar wave that is being sent. Now, there is a property of radar that you can modulate the frequency on a linear array, and that allows it to look to the left, to the straightforward, to the right. So by modulating the frequency of that linear array, this set of antennas can sweep an angle of about 120 degrees in the ocean. And that, of course, is important in terms of finding incoming waves from several angles, for a broad range of angles. So this is what the thing looks like. Here are the 4 transmitting antennas. Notice that it is pretty close to sea level, the system actually works best when it is very close to sea level, because remember, the radar wave is going to hug the surface of the ocean. And here's the array of receiving antennas. There's the little place where they process the data. And then a very efficient system. Okay, so what do they measure? So remember that we had the Bragg diffraction, and that brings two peaks of refracted energy, and that's what these ones are. The decibels is the strength of the signal. So there's going to be a certain frequency, say the blue color, in that is going to be the first order peak. And there's another one here, a second order, that would be that reddish color. There is, of course, there's a little purple and a little yellow there, and there's a little blue in there. Those are those secondary peaks that are here in the response. So what the radar is measuring is it is measuring that Doppler peak. And we know exactly where it is because we know that we're bouncing off waves that have a 5-meter wavelength. Now, if the wave doesn't have that new push because of the tsunami, the position of those peaks is pretty fixed. But if the incoming wave is being scrunched because there's that additional push by the tsunami, then those frequencies are going to change. And they're going to change symmetrical to that 0 point. So please remember these numbers: 0.52 for this peak and minus 0.52 for this peak. And let's see what a signal from an incoming tsunami looks like. So there it is. It is Doppler shifted. Over here you have the response, the decibels, and in a way that is a proxy for distance. And so at a distance of 146 kilometers, you start seeing those two peaks, right? And as they get closer and closer, the peaks are well defined. And notice that now this has shifted to minus 0.25 and 0.25. That's the indication that that wave is advancing a little faster than in a sea that is uncoordinated, that has no preferential direction of movement. So that's what we're looking for. Now, this is as a function of frequency. So you're seeing the frequency of the Doppler peaks, and it's the shift from that 0.52 to 0.25 that tells us that you have incoming waves. Now, this is something similar. In this case, you have the range and you have time. And in this case, if the wave is moving toward the source of the radar, you have the hot colors. And if it is moving away from the radar, you have the cool colors. So notice that at 4:45, you started seeing the presence of a push in and a move away. And then by the time you were in at 5 hours, there was a definite pushing in and moving out of the Doppler frequency. And by the time you're here at 6 o'clock, you are definitely on that very strong push and pull, showing that the wave is either advancing a little faster or retreating a little faster than would be normal if there was no preferential movement. This is a tide gauge that was nearby. This, by the way, is from Chile. And you notice that at 4:30, the tide gauge showed kind of a little bump. And then at 4:45, there was a significant increase, maybe 0.7 meters. And then there was a decrease. And then there was another increase. By 5 o'clock, the tide gauge was recording up to a meter in displacement. And by the time it was 5:45, then we got the main peak of the tsunami with displacement of about 2 meters. Note to self, tsunamis come in different waves, and the first one is not necessarily the biggest one. Okay, and here is a different radar. This is from Figueira in Portugal, and this was a meteorological tsunami. I forgot to mention that in the first slide, that sometimes storms are strong enough that they lift the surface of the water if the low pressure is significant, and then they drop it, and that drop is enough to create a tsunami wave, a very modest tsunami wave, and that's what happened here. But you can see the 120 swath of the radar. The little arrows are velocity vectors at that particular time, but there's that peak in velocity toward the radar, and notice that there's away from the radar, toward the radar, away from the radar, not much, away from the radar, toward the radar, and so on and so forth. And that's what we're looking for. Now, this is Sumatra, this is Padang, and remember that the slowdown of the wave is what causes that increase in amplitude and that forward push, and particularly prominent after you reach a depth of 200 meters. Now, in the case of Sumatra, we have a relatively short coastal shelf. You have depths of about 3,000 here, rise to 1,500, and then by the time you're on the west coast of Siberut, you reach that 200 meters, so maybe 150 kilometers out. But then you get into the Mentawai Trough, and the depth increases again, so that's going to be a problem. By the time you hit 200 again, you're very close to the coast, and that doesn't give you a lot of time. If you imagine that this is moving at 35 kilometers per hour, if we had a large shelf, we would have more time to forecast the arrival of a tsunami wave. The other thing that is interesting here is that over here, the water level is, or the depth to the ocean is very shallow. Now, what happens is if you have an earthquake propagating or an earthquake triggering a tsunami on the north end of Sumatra, that wave is going to have to sweep south on this very shallow water. And that is going to be different than that wave that was heading straight toward the shore. These are simulations by the Pacific Tsunami Warning Center of the propagation of the 2004 tsunami. It was generated in the northwest end of Sumatra. And you can see that, well, it's beginning to break into a series of different waves because of the irregularities of the seafloor, but it's beginning to move south along the west coast of Sumatra. After a while, it has swept south. Now it's hitting head-on Sri Lanka and the east coast of India. But then after a while, as far as Indonesia is concerned, it has turned the corner, and now it's going to begin sweeping Java from west to east. And also it has turned the corner in India, and now it's going to begin sweeping the west coast of India from south to west. This is something that we normally don't think about. The fact that a tsunami is a force wave when it is in the coastal shelf that is moving subparallel to the shore. This is the case of a meteo tsunami. It was caused by bad weather that hit the Dutch coast, but you can see that it's definitely pushing its way along the coast. Now, this is a little complicated, and it's very hard to model it, but I think it's good news for you young people, because as you get to use these tools, you realize that not all the problems have been solved. There's going to be the need for further research so that we study what the approach along the coast is in this type of method. And then I want to remind you that the key here is to collect enough scientific information that we can provide a useful product to the civil authorities. This is normally going to be the best science we can do, plus a probability assessment of how confident we are on our data, so the civil authorities can take action and protect their communities. The final goal that we have here is we want to protect the coastal communities. This is the end of the talk. I want to thank my good friend, Professor Di Corita, Director of STMKG. She greatly facilitated my visit to Indonesia in August of this year. I have known Professor Di Corita for 30 years, so this is a good old friendship that we are renewing. I also want to thank Dr. Swaidi, the chief of Padang Panjang Station, BMKG, both because he was my traveling companion through Sumatra and because he introduced me to this fascinating aspect of tsunami monitoring. I consider him my mentor in this regard. Professor Dimas with STMKG, of course, is my partner in crime. He and I are trying to get this lecture series going, and I'm very grateful for all the work that he has done. Professor Suko, the acting director of STMKG. Professor Suko and I are of an age, so we became instant friends, and I hope that one of these days we'll have a chance to go and travel through the Sulawesi archipelago and discuss all the issues that are present there. And then finally, a great deal of thanks to Roberto Gomez with Helsel Mess Technique, who spent a lot of time introducing me to the intricacies of high-frequency radar. He basically gave me a half-hour private lesson so that I could get started. There's still a lot more work to do in this area, and I look forward to do that. Some important references, and I think I sent to Professor Dimas a copy of this paper, which I found particularly informative. Also, you have a couple of websites that I think are very useful in terms of understanding radar in general, and then the high-frequency radar that I described in this talk. And that, folks, is about it. Let me see the chat.
Okay. Thank you very much,
Okay.
Professor Horacio, for your very nice talk and a very interesting lecture. We are very happy to hear that. Indeed, you are a good friend of our director, Professor Dwi Korita, and our Professor Suko. Now, Professor Suko is joining us. Good morning, Pak Suko.
Morning.
Thank you for
Good morning,
joining us.
Professor Horacio. How are you?
Hello, Suko.
Hello. Thank
Maybe
you
we
very
can
much.
hear a little from Professor Suko. Pak Suko, silakan Pak.
Yeah. Thank you very much, Professor Horacio. You okay?
Yes.
Thank you for
I am
your
in very fine shape.
Yes. Okay. For Professor Dr. Horacio, thanks very much for your guest lecture in this morning. Assalamualaikum warahmatullahi wabarakatuh. Let's ask me grateful to Allah because we have been given health and protection, so we can gather to carry out of the first guest lecture and field geology and dynamica, delivery by Professor Dr. Horacio from California State University, Stanislaus. Professor and all participants, I really support for this activity, and it has even become a priority for STMKG program as one of the strategy to become a world-class higher education institution. For this, I hope this activity is continued regularly with lecture from California State University and other university related to scientific discipline and field meteorology, climatology, and geophysics, and instrumentation, meteorology, climatology, and geophysics. I hope STMKG lecture and cadet continue to be part in this program so that we can share knowledge and skill. If possible, STMKG lecture and cadet will one day become guest lecturer at other university both in the world. And I hope the quality insurance unit, research and community service unit, and well as head of study program within the STMKG continues to prepare a more scheduled and well administered guest lecture implementation schedule. Professor Horacio and all participants, I want again thank you for holding this activity. I hope that this activity will become a field and clarity for all us. Amin. We say Bismillahirrahmanirrahim. I declare that today the guest lecture event has begun. Thank you.
Thank you.
Thank you,
Thank
Professor.
you. Thank you.
Thank you very much, Professor Suko, for joining us for this today lecture. And indeed, we will continue the cooperation between California State University and STMKG, and followed by many activities between the two institutions.
I'm sorry. One minute, Pak Dimas.
Professor,
I'm sorry. Professor, I hope if you have friend and sometime come to Indonesia, you okay and your friend you okay to come to Indonesia, I hope to call me. We get together for discuss in here and we go there together to round to Jakarta maybe with me. Okay, Professor. You have plan next year? Come here or your friend?
Well, right now I'm thinking going back to Indonesia in the summer of 2025.
Oh, 2025. Oh, maybe
In the
next
summer
year.
of 2024, I'm going to be in France.
2024. Thank you, Professor. Okay, continues.
you can go together to France next year.
Yeah,
absolutely. Hey, join me in France. We'll
You can
love
meet
it.
in Europe.
Yeah. Okay. Thank you. Continues. Yeah.
Thank you, Professor Suko. Now I want to greet faculty members of STMKG. Here we have Dr. Wandono. Good morning, Pak Wandono. Pak Wandono is the head of Department of Geophysics.
Morning, thank to Professor Horacio
and Pak Joko. Pak Joko is the
Professor
head of the
Suko.
Department of Instrumentations. Good morning, Pak Joko. Yes, and we also have Pak Puji. Pak Puji Arianto is the Vice Rector of STMKG for Student Affairs and Cooperations. Good morning, Pak Puji.
Good morning, Prof. Dimas. Good morning, Prof. Horacio. Nice to see you again.
Good morning. Good to see you all again.
And also we have some faculty members of STMKG, Pak Mahmud Yusuf. Good morning, Pak Mahmud, Pak Januar Arifin. And also some people from geophysical stations. We have the staff of geophysical station of Padang Panjang.
Hey,
the leadership
my friends.
Good morning for people from Padang Panjang geophysical stations and geophysical station of Balikpapan from Borneo. Good morning to all of you.
Good morning. I'm so glad that you were able to join us.
And also Dr. Ratri from Institute of ITENAS from East Java. Good morning for joining us.
Good morning.
Thank you all for joining this guest lecture. And now time for questions and answer. We have some questions from students. First from M.Si. Time is yours. You can ask your questions directly to Professor Horacio.
Thank you for this opportunity. Thank you, sir, for this opportunity. I want to ask a question. Does the high-frequency radar monitoring can estimate the velocity and the height of the incoming tsunami when it hit coastal area? Thanks.
I'm not sure I understood exactly. So say that again, please.
Okay, I will repeat it. Does the high-frequency radar monitoring can estimate the velocity and height of the incoming tsunami when it hit coastal area?
No, we're not measuring wave height. We're measuring that incremental increase in velocity. So the velocity would have to be estimated from that graph that measures depth with respect to velocity. And of course, it's going to decrease as the wave gets closer and closer and closer. Ideally, I mean, it's a good thing that slows down. But no, this method would not allow that. Neither the amplitude nor the actual velocity of the wave train to be estimated. It's that incremental velocity that we're measuring.
Thank you. Is it answering your questions? Are you okay?
Very answering, sir. Thank you.
Okay. And next, Fawaz, time is yours.
Good morning, sir. I have two questions. First, is HFR has a limitation range to provide accurate data? And the second is is like a storm can disturb the HFR radar?
Well, the whole method of high-frequency radar was designed to observe the ocean for shipping. So its original purpose was to determine roughness in the ocean and different conflicting currents. For that, you normally need at least two different radars looking at, say, for example, the Sunday Strait. That's a perfect application in which you have one station in Sumatra, one station in Java, and they're both looking at the strait. And from there, you can figure out what the velocity of the swell is and what the directions of the swell are. And yes, identifying the arrival of a swell from a nearby storm is important. You can actually see, there may be a raging storm, and you can actually see through that. That's one of the beauties of radar. Whether you're going to be able to separate the signal, that's more of a question. Remember, a very complicated sea has embedded in it a wavelength that is half of what you're emitting with the radar. So yes, there will be reflections, but whether the reflections are going to be coherent, like it would be in the case of a tsunami, or they're going to be little peaks floating in that color graph, that I cannot tell you. At this point, I would say we need to observe the ocean more with this type of system so that we can get better at identifying what the return and the responses are.
Thank you very much, sir.
Thank you, Professor Horacio. And next question from Lutfi. He's asking about the Doppler effect. And is it only the backscattered signal from the tsunami wave that can be Doppler shifted? How about other phenomena in the oceans? Can it be Doppler shifted?
Yes. For example, in meteorological tsunamis, it's actually the blow of the storm that is propelling the water forward. So you would also detect that. Now, whether you want to call that a tsunami or not, I mean, some people would just call it a base surge. But yes, you ought to be able to detect that.
Okay, and then from Fahrul Surya, time is yours.
Thank you very much, sir, for the time. and thank you for the presentation. It was really amazing and enlightening us. I will ask one thing. I'm not really an expert in this field. Are there any advantages in using high frequency radar to monitor ocean current compared to other methods?
Well, ocean currents change a lot, so you can always try to measure them with a device that is floating, but maintaining hardware in the ocean is very difficult. So particularly if you have two different radar stations, it's a lot easier to measure the vectors that the ocean is having toward each one of those stations, and then by vector addition, figure out what the currents are. It only looks at the surface, though. So if you have a longshore current, for example, or a rip current that is below the surface, radar cannot detect that. I see in the chat 2 questions. Martha wanted to ask, are there any changes that HF radar can detect, or is there any chance that HF radar can detect a tsunami cause? No. However, HF radar may be the one thing that we can use to detect landslide-induced tsunamis or submarine eruption caused tsunamis, because those ones don't come with an earthquake. Whenever there's an earthquake, we use all the seismic equipment and say, hey, look, there was an earthquake. But if there's a landslide, the landslides are normally not very noisy. And so our first intimation that such an event has happened may be with a HF radar. And in that case, you will have only a couple of hours. It's not like with an earthquake that you may have 24 hours. If it is a landslide or a volcanic eruption, your response time may be much reduced. And then you have another question, Martha. If the HF radar detects a high notification of tsunami, what is the process to warning people about the tsunami in the WERA system? Now, very specifically in the WERA system, they are aware that there's a certain probability that that increase in velocity is due to a tsunami wave coming in. And they try to double check it, knowing that it's not only one wave, but it's different waves coming in. So the results are shown in terms of probability. And I know probability is not a very satisfying solution to people that want yes or no. So it is up to the civil authorities and to the analysis center, like you have in through BMKG, to determine if all the probabilities of all the observations are high enough to turn it into a yes, go ahead and evacuate, or no, the probability is too low. So in that sense, it's a statistical approach to help the civil authorities make a determination. And then Angun also has some questions. As we all know, the HF radar is one of many other tsunami monitoring methods. Is there any possibility that the monitoring isn't optimal because of any factors? Because as I've been known before, that BMKG has radar with a different appearance on tsunami monitoring area. Yes, it is possible that the orientation of the antennas is not optimal. For example, I did mention that if you have a tsunami wave moving through the coastal shelf from north to south, and we're looking to the west with the radar, we're just kind of on the side observing it. So it would be convenient, it all costs money, but it would be convenient to have more than one installation that is looking, one is looking to the north, one is looking to the west, one is looking to the south. Because conceivably, earthquakes would be generated in Java, and then they would be propagating up the coast to Sumatra. In that regard, the WERA system may be kind of the Cadillac version of a radar system. There are other companies that produce more compact radar systems. They're not as versatile as the WERA, but they may be less expensive, and you may be able to afford having several of them so that you're indeed looking at different directions to try to catch this approaching waves. Two, also from so far, is HF radar the most effective method for tsunami monitoring? I'm going to say no. I think that the most effective are sensors, pressure sensors in the bottom of the ocean, but they are extremely expensive and extremely difficult to maintain. So even very wealthy nations like the US or Japan, they probably have 20 sensors each. And the Pacific Ocean is a very large ocean, you know. So yes, hopefully at some point Indonesia can maintain a series of pressure sensors, but it's probably going to be 5, 10 in the best of cases, and they have to be maintained. You know, they cost a lot of money to install, but then once a year they have to be visited or brought to the surface, make sure that they're in good shape before they're installed again. And that is very, very expensive. I would say that HF radar is the best compromise right now between cost and efficiency.
Next questions from Adedo Ikdai. You want to ask questions?
Yes, thank you, Mr. Dimas, for this opportunity. Good morning, Mr. Professor Horacio. I was interested by your statement that the northern areas, the northern Sumatra has a different wave propagation because the area is shallower than the southern. So I was curious, what about the eastern part of Indonesia? If we put the HF radar in that, is there many of the different of wave propagation? Because as we know that Eastern Indonesia has more complex structure more than Western Indonesia. Thank you.
Absolutely. You're absolutely right. The Sulawesi archipelago is a serious hazard, seismic hazard, tsunami hazard to the populated areas of Borneo and Sumatra and Java. Historically, they haven't had an event, whereas the Indian Ocean side of Indonesia has historically experienced much more tsunami hazards. That's one of the reasons why I want to invite Dr. Suko to join me in the summer of 2025 to visit the Sulawesi archipelago, because I would like to see what the situation is there. The one thing that we know is that the ocean around the Sulawesi archipelago is very shallow. So the volume of that ocean basin is small compared to the volume of the Indian Ocean. And even if you were to throw a very large rock in the Malacca Strait, that ocean, you are probably not going to generate as large a tsunami wave as you would in the Indian Ocean. But honestly, I'm a little out of my depth there because I have not studied or seen that part of Indonesia.
Okay, indeed, we have a lot of questions. How about from professors or faculty members of STMKG? Do you have any questions? Okay, if not, maybe we can stop here, and we thank you very much for Professor Horacio.
Let me just do one last thing, please. Let me share my screen again. There you have my email, hferriz@csustan.edu. I do answer my emails. So if you send me an email with a question, you can count on getting an answer within certainly a couple of days. Okay, so please take into account that I can be reached, and I am very glad to communicate with the faculty, with students.
That is so very kind of you. Thank you very much again. And for students, if you have any further questions, just send an email to Professor Horacio, and he will be happy to answer for your email. Okay, and now we have a photo sessions. So please open your camera. We'll have a photo sessions. And Rizal will help me. Rizal, are you there?
Semua suruh buka, Mas. Yang nggak buka dimatiin aja.
Please open your camera.
Ya, kalau yang nggak mau buka dikeluarkan.
So I want you to know that we have 107 people in this talk.
More than 100.
Ratri suruh buka, Ratri.
Yeah. Okay, open your camera. Rizal, please help.
Yes, sir. Excuse me, sir. In slide 1. In 3, 2, 1. Okay, next slide. In 3, 2, 1. Okay. In next slide. 3, 2, 1. Last slide. 3, 2, 1. Yes, sir.
Excellent. Well, a pleasure seeing you all. And
perfect.
Next semester we'll have another talk. Hopefully, Dr. Shadows will be able to join us.
Thank you, Professor Horacio. Thank you, Prof. Suko.
Thank you, Professor.
Goodbye.
Thank you, Professor
Good seeing you
Horacio.
all.
Pak Puji, Pak Wandono, Pak Puji.
I
Terima
bet
kasih, Pak.
you come again to Indonesia.